Good afternoon and welcome to Computer Vision today. There were some questions about the start today. I had notified you last week that today we're starting half an hour later because I had a parallel appointment. So in last week we started with this lecture, and I will always provide a quick revision of the previous lecture, just that we are all on the same page. Last week, we looked at what the field of computer vision actually is. We saw applications. We discussed the organization of this course and the schedule. We then talked about some of the recommended literature in addition to the slides. And we saw that computer vision has an intersection with lots of other disciplines. We saw what's the relation between image processing and computer vision, and we saw that computer vision is the exact opposite of computer graphics. So computer vision, computer graphics, just the opposite. We saw a couple of examples why vision is so tricky, and we discussed the three levels of vision: low-level vision, intermediate, and high level. We started last week with edges and pixel operations or low-level vision. Today we'll talk a little bit about regions, so segments, but we will also go back to some low-level vision, which are corners. That's plus some other features. So today we will operate in these two levels. And we then discussed briefly how digital cameras discretize the real world, and in multiple ways, like what we can see here, both along the shape as well as along the intensity, we have a discretization. Pixel images can be represented simply as a matrix, and we mainly work with grayscale images where a pixel value 0 would be black and 255 would be white. So we have 1 byte per pixel. And there are also different color models that we discussed, as well as the famous Lena image here. And we noticed how noise can be visualized in these images. And then we discussed the local average filter to wash out the noise, which removes some of the noise, but also removes the sharpness of other properties like edges, which comes with new consequences. There are lots of other noise filters, obviously. We saw this local average filter is eventually just a specific two-dimensional convolution, but we don't care about these integrals here, since this course is taught in a computer science department. We like to have discrete data, so our convolution can be expressed as such an operation or simply in this matrix notation. And we saw different operations, as well as then had a case study of how we can actually detect edges. And for this, we built the Sobel operator and visualized it and briefly looked into the Kenny edge detector. And we also saw some code examples of how you could implement this with scikit image as one example. Plus, there are obviously many other more advanced edge detectors. But that was what we did last week. And today we will do two chapters. We'll move now a bit into intermediate vision. We'll look at regions of images and segments. Then we'll go back to finding some more features in images. In particular, we will study corners today, plus a couple of other features. And then we have all the framework ready to start looking into object recognition in the next lecture. And there are lots of approaches to object recognition. For example, convolutional neural networks that will be studied in detail. I had sent you this round mail, and I had corrected it because I had put in the wrong month, but now with the update, it's correct. So next week, and I'll say it here orally again, so that we're all on the same page. Next week, there is, on the Thursday, it's a lecture-free day at Deggendorf Institute of Technology because of the upcoming Easter holidays. However, the following week, so in 2 weeks from now, April the 9th, we will have an introduction to this Cronus challenge. And the lecture on April 9, all of you are required to attend live through the video stream because at 2 p.m. the Cronus colleagues will present their challenge, and many of you will pick this as a project. Even if you want a different project, you have to attend that session so that you just know what's going on, and they will reveal some information, and there could be some more general questions about the project as well. So that's in 2 weeks' time on April the 9th. However, in order for you to understand what we are discussing with Cronus about their challenge, we will have a lecture next week as well, even though it's a lecture-free day, but we'll have the lecture as usual at 2 p.m. And if you can't join live, there'll be a recording for you anyway, because next week I want to discuss object recognition and convolutional neural networks. So we're well prepared for the Cronus challenge. And the Cronus challenge, when it can be presented, I'm simply subject to the availability of the industrial partners, and that's in 2 weeks' time. So we need to make sure we have the necessary foundations. So that's why we'll have the lecture next week as usual at 2 p.m. and we'll look into object recognition and convolutional neural networks. Are there any questions from you so far about the organization or the content or anything? If there is any questions, you can turn on your mic or you can just share the questions here in the chat and I'll be happy to respond. I'll see if any questions come in or not, but I'll start talking now about the next chapter, regions of images and segmentation. So we will see what segmentation is. There are lots of segmentation approaches, like perceptual grouping. There's also Gestalt theory, which comes more from psychology. And we will see how all of these approaches can help us to find segments. And then we'll have an application from image processing. We will have one segmentation approach, concretely a clustering algorithm, and that one we will apply to image compression. So you'll see how you can actually compress an image with a relatively simple algorithm. That's this chapter. So our goal in segmentation is, so far we have seen pixel images, and we've purely looked at individual pixels. Now, we want to identify groups of pixels that actually fit together. And so we want to separate an image into these coherent regions or objects, but they are not actual objects that we want to recognize, but say we want to separate the image into coherent segments or regions that could be seen as an object, but they're not necessarily an object, but something for further processing. So segmentation oftentimes serves as an early step in a bigger pipeline, for example, for pre-processing, so that we would have an image, we would find different segments, and then the identified segments, they would be processed further, say for classification or something else. Now, here's one example of what we want to do. We have this color image here, and it's an RGB image. And what we want to do is we want to separate all the objects from the background. So these are cells, and there are some cancer cells, as we can see as well, some bigger ones, some smaller ones. And what we want to do is we want to separate all of these objects from the background. So what we do is a so-called binarization. So that means it's either background or an object. Now, I want to know from you if you have any idea of how we could actually do such a binarization. So we have a color image and we need to transform it into a binarized image. If you feel you have an idea of how this could be done, maybe just send a thumbs up or thumbs down if you don't, and if there's any positive response so far. So we got one person, that's great. You can just turn on your mic and tell us how you would do the binarization. And I've seen you've muted yourself. Go ahead.
Sure. So since the background is white, if we detect in the RGB, there are three layers, right? So if we detect there's color other than white, we can just switch it. We can convert it into black. So that way, instead of three matrices to store R, G, and B values, we can just have either one or zero for white or
Okay.
black.
But how do you determine if something is really white? Because the background is not perfectly white, as you can see. It's maybe a little bit bluish or something. It's not, the
Can
background is not perfectly white.
we can get the value of, of what the background color is
Okay, but
from one of the pixels.
that keeps varying throughout the pixels, also due to illumination and maybe some noise. Not all the background pixels have exactly the same value.
Okay.
But it's a start. Anyone else has an idea of how this task could be done? If so, maybe raise your hand. I'll see if there's anyone. But the initial idea was good. We would pick like the background value and filter everything else out. Yes, but the background value here is not perfectly wide. One person suggests normalization in the chat. Maybe you can tell us more what you mean. And then one other student suggests we find a threshold. And the thresholding approach is also what I would do. First of all, I would take this RGB image and convert it to grayscale. And we've seen this last week, how we can do this. So we just add, for each pixel, we add up the and RG and B values and divide that sum by 3. Then we have a grayscale value. Now, this image would be converted to grayscale, and then we would need to find some threshold because the background is not perfectly white. Um, Say we've said before 255 would be white, and 0 would be black. So, but these pixels here are not really 255. They may be 220, for example. So we would need to come up with a threshold, and everything for example, above the threshold, like these pixels here, they are maybe 220, 230. If the threshold is, say, 200, for example, everything, or we pick a different threshold, say we pick 150, for example, everything that is 100, greater than 150 gets mapped to 255. So these pixels that are greater than 150 would become 255, and all the other pixels that are under the threshold or equal to the threshold, they would be mapped to 0, which would be black. Now, you could try 150, maybe you get your desired output, maybe not, so you would probably have to adjust the threshold a little bit. Maybe it's not 150, maybe it's 180 or 200, I don't know. So you would do this as an experiment, and this is how you would determine your threshold. So it's two steps, as I said. First, we convert RGB to grayscale, and then we apply the thresholding. And now we have this binarization, and then these objects here, or these segments, they could then be further processed. For example, we pick this segment here, and this would be passed to some object recognition algorithm, maybe a neural network, maybe something different. And this would be classified into the cell is fine or the cell has cancer. Um, and probably what we would see somehow size is something that could be used for the further classification, like these very big cells here, they are cancer, or very, very small ones too. But this would be a later step, and we're doing object recognition next week, not this time. And that's how I would approach this problem here for the segmentation. So a simple binarization. Um, then obviously there are way more sophisticated segmentation examples. For example, we have an autonomous car that is driving through this road, and what it sees is this scene. And so far, we don't care about yet what is a car or what is a house, but we just want to build segments. So we want to keep the pixels together that somehow fit together. So obviously here is some segment while here is another segment, and maybe that's even a different segment. So we would need some algorithm that can do this for us. And then in the next step, we would classify the segments and see whether, for example, a neural network would take this segment and then classify it as a car. So what we see down here as the solution or as this table for our colors, they already provide a label, but that would be something coming from a later stage. What we first care about in a segmentation is getting an image like this, where we have the different segments, and then they would be processed further. Now, how can we actually do segmentation? So there are lots of different approaches, and here's actually a lot of text, but this is mainly for your revision. And so you can do this for further reading, but I'll just tell you a little bit how I would suggest how we can build segments. For example, segments can be built if when pixels fit together, maybe based on their color or based on their intensity. That could be some approach, or we could try to find some specific shapes in the segments. Maybe we want to keep pixels together with a constraint that we want rectangles or squares or circles. Something like this could be an approach for segmentation. So there are many, many different ways how we can do the segmentation. And we need to define some criteria of what fits together and what does not fit together. And fitting together could be intensity, colors, something like this. And now we need to build such segmentation algorithms. We will start with some that are inspired from psychology or philosophy as well, and later we will see some machine learning approaches. Sometimes what, as an early approach for segmentation, this would go back to something called Gestalt theory. This is work that was done by Christian von Ehrenfels in the late 19th century. And it's a whole school of psychology, actually. So we'll only look into it for a few minutes, but we will maybe derive some rules or some approaches from this. And the Gestalt theory has this assumption that when you have a whole thing, and we will see examples soon, then this whole thing would contain more information than just a sum of its parts, because you have a bigger whole thing, and that would provide you with more information than if you just sum up the information of its parts. And there are lots of examples from Gestalt theory. For example, maybe you have seen this kind of stuff. When you look at this example, you would intuitively sort of think that that line here is longer in the upper object than in the lower one. Who of you feels just from looking at it? So we'll do some voting without obviously knowing the solution, but just looking at it the first time, who would feel that this line is longer than that line? If that's the case, maybe send a thumbs up. If you feel it really doesn't look longer, you would send a thumbs down. But I guess it's made this way that you would feel that this actually looks longer, but it's not. And it has to do with these outer parts. So if they're opening to the left and right, this would intuitively seem longer than if they're closing to the left and right. But they're just the same length. And there are other examples, other perceptual phenomena, like this one here. You would assume that this inner section is sort of longer, or like the or not the length, say the height. So this one here, the height, so the distance between the first line and the second line, that distance here for the upper image or for the upper object is bigger than for the lower one. If you also feel that this distance here is longer than in the lower one, maybe send a thumbs up or thumbs down just from the perception. So one person disagrees. But I think a lot of people, when they see this the first time, think this one here is sort of bigger than this one, simply because here they are opening, they're wide, while here it's focusing. But I don't see really that you, well, I see some agreement, but not too much agreement. But these examples are made up just using or exploiting how we as humans tend to interpret this. Now you wonder, why is this important to computer vision? Because this Gestalt theory, there are lots of different so-called laws. And when this Gestalt theory was proposed in 1890 or so, it had nothing to do with computer vision. It was simply from a perspective of psychology. But it turns out that these so-called laws, they could be used also when you build a computer vision system and you want to add some rules to a computer vision system. Maybe some of these laws could be exploited. So there's the law of proximity, similarity, good continuity, closure, symmetry, simplicity, and common fate. We're just looking at, I think, two of these laws. So if you're curious about Gestalt theory, feel free to look up more of these laws. It's just briefly to show you how we as humans tend to perceive things, and then in a moment we will see how this could be exploited in a computer vision system. So the law of proximity says that it's about stimulus elements which are closer. They tend to be perceived as one entity. So we have an example here. So we have these objects here and these squares, and we have it's like a matrix. So we have rows and columns, but we see that in each row we have them close to each other, and there's a not row, sorry, in we have this column here and we have another column. So they're very close to each other within the column, but there is a distance between the columns. So we have this distance here between the different columns. And then we sort of would intuitively perceive that the way we have this structured here, that we have groups, concretely columns, and we have a group of elements in here as well as in here. And we would rather assume there's a group per column, and we would not really assume there's a group per row like this. If you also feel just intuitively by looking at this that we have these groups in the column rather than in the row, maybe you would send a thumbs up or a thumbs down if you don't agree. So I see lots of agreement. And then there's another Gestalt theory law. It's called a law of similarity. So what does this mean? And it says that similar elements of a stimulus, they tend to be part of a unit. So when we have, again, this matrix here, we have circles as well as squares. We could try to perceive units in here, but I think a lot of people, they would tend to build units here in a row and say this is a unit, so all the circles, then all the squares are a unit, and we have another unit here. And so we would rather assume to group them based on their shape rather than building groups here in the column. If you also think you would more intuitively build the units here in a row, we cluster them ones that have the same shape, maybe send us also a thumbs up. So I see lots of agreement. Now, you're wondering, what is this useful for? So it comes from psychology, but in fact, this could be used in computer vision, and some computer vision systems take advantage of this. So with these rules, imagine, or these laws, imagine we have a vision system and it needs to recognize certain objects. And if we sort of know maybe which sub sections or which regions could be in an image, and we could somehow detect maybe, for example, these segments more easily, we could build some rules based on these segments and how they fit together in order to describe rules and later recognize whole objects. And this could be done, for example, if we have a controlled environment where we don't take photos in the wild, but maybe in some controlled manufacturing process or some other controlled process where we don't take photos in the wild, and that maybe there are certain objects in it, and we could infer based on the possible objects that we have in there, bigger units, and we could sort of build rules that a computer vision system would infer based on these Gestalt psychology laws from that. Um, that could be done, but it's something used in some vision systems. However, probably most vision systems today, they are more sophisticated. Like we use things like neural networks, and we actually try to learn such properties from data, and we don't describe this as rules from this Gestalt psychology. That's why I just briefly mentioned it, but I think it still provided us some insights of how we as humans perceive things, and that could always be an inspiration for certain vision systems. But now, actually, we will look at more concrete segmentation algorithms, and we will also later see a concrete machine learning algorithm that we can use for segmentation. So in the literature, probably thousands of segmentation approaches have been proposed over the last few decades. So they all aim at identifying some some regions in an image, and the pixels in that region, they share some common property, be it color, be it intensity, be it shape or whatever. And most of these segmentation algorithms in the literature, they can be categorized either as merging algorithms or splitting algorithms. And so, what is the difference between merging and splitting? These merging algorithms, they would actually start with single pixels, and then they try to increasingly merge more and more pixels from the neighborhood, in as long as they still have that property or they are close enough in some properties, we try to merge them into bigger and bigger regions. So the merging algorithms, they would be a bottom-up algorithm because we start with very simple pixels and then look at their neighbors and keep merging until we stop, until we find new pixels that don't really match these criteria. So it's a bottom-up approach. The other approach are splitting algorithms. So they would start with a very big region that is non-uniform, maybe like the whole image, and it would try to increasingly break this non-uniform region into smaller regions until they are uniform, and then we stop splitting. And that would be a top-down approach because we start on the top with the whole image and try to break it into smaller and smaller regions. There are also combinations of merging and splitting. So there are some algorithms that combine both of that, which we will also see in a moment. However, in all of these cases, we need to define the uniformity criterion. So we must define what's actually uniformity. So what is a property that some pixels still actually belong together? Maybe we need to define this based on intensity, color, or whatever. But these are just some possible approaches. And sometimes we need to define some thresholds for this as well. And we probably need to test this on a couple of examples to see if this works. There are also approaches like that allow us to do a segmentation by the histogram. Last week we started looking into pixel images, but I don't think we've introduced the concept of a histogram yet. So I will show you this and then we'll see how we can use histograms for segmentation. So we have a pixel image and it's in grayscale. So it's 1 byte per pixel. That means 8 bits. And that means we have 256 possible intensities among the pixels because it's all value, say value 0 to 255. And with a histogram, we would go through every pixel and we would count the intensity of each pixel. So the first pixel maybe has intensity 10, the next pixel has intensity 50, and we'll just go through and count for every intensity 0, every intensity 1, every intensity 255. So from 0 to 255, so 256 different bins are needed. And this can also be visualized. So we have this leaf here, it's a grayscale image, and we see there are not really many pixels that are totally black, not much. But we see there are quite some pixels that are relatively bright, which is the background, and probably the outer area of the leaf. They are not perfectly white, but relatively bright, which means we have a peak here, which there are a lot of pixels that are somewhere between 235 and 245. That's why we have this peak in a histogram. And then we have a peak here, but it's a bit flattened out where we have a lot of pixels, say between intensities 100 to 160. And these are most of the other pixels in here. And we can calculate this histogram just by counting the intensities. Are you all okay now with the concept histogram? Maybe just confirm if you got the concept of what we are trying to build here. So maybe more thumbs up or thumbs down if you didn't get it yet. But everyone seems to be fine so far. And what we can do then is we can try to use this histogram to build different segments. So what we could want here is, for example, we could try to split the leaf from everything else. Like we want to get to this solution here. Here we would see that the background is very bright, but the pixels of the edge of the leaf, they are not that bright. So we could try to build sort of a range, maybe something like this, where we could say all the pixel values from 0 to 240, for example, only those are supposed to be visualized. Then we would visualize the actual leaf, but what we see here in red is the background that is visualized. So that to visualize the background, we would only take the range of, say, as of 240 up to 255. And we only visualize the pixels that have an intensity in that range. And then we can try to filter the background out from the rest. We could also try to filter the dark part of the leaf, which would be probably everything around here, around this peak, and that would be largely the pixels of the leaf, except the edge of the leaf. And for the edge, we would need maybe something like this between, say, 180 and 240. That could be maybe the pixels which are the edge. So we can simply just calculate the histogram and then try to define ranges in the histogram and use this for segmentation. Do you think this approach looks okay for this example here? Do you see any issues with it? Any benefits? Why is this approach maybe so interesting? If you have any comments, I'll give you a moment, send them to the chat, or There was a question. I only saw this. What does the x-axis stand for? If I don't see your questions, always just turn on your mic. The x-axis here is just the intensity. So intensity 0, intensity 1, intensity 250. And in the y-axis, we have the occurrence. So how often that intensity has appeared within the image. Hope this has resolved the issue. So the histogram approach has one big advantage. It's fairly easy to calculate. And it's very fast to calculate because all we need to do is we only need to count intensities, calculate the histogram, and if we define the thresholds once, and we know it's a sort of controlled environment, we would just apply these thresholds again, and then we would only visualize the pixels which are in a certain range between two thresholds. So one student says that this method seems useful here because we have these two peaks, so we can find the thresholds easy. Yes, and we can interpret it, we can calculate it extremely fast, so we don't need a high-end GPU for that. However, this is sort of an ideal condition. Imagine we add noise now. This was the original image, and we add salt and pepper noise to it. And what we get is that these peaks are really sort of starting to get washed out. The x-axis is still the same, 0 to 255. And on the y-axis, you just see it's a different scale because this was separated so well. So there were a lot of pixels with a very high value. And we had this peak here, but if I put a salt and pepper noise, we just wash this out a lot. So we see we have a different scale on the y-axis now, and it's all sort of just spread out throughout this interval. And using this approach now is more difficult because if I say I take, like before, values in this range, this helped me to just visualize the leaf, but now I would also visualize some of the noise outside the leaf. So I would probably not be able to apply a proper histogram segmentation to this image here, but rather I would, after the salt and pepper noise, I would probably have to do some local average filter or some other technique for blurring, and then I would try it again. But if I blur too much, I will also I will lose the sharpness of some of these properties. So tough game. So we see when we have real world images and there are lots of sources of noise, like illumination, for example, then the segmentation approach via histogram starts to get more difficult. We can obviously complicate the setting a lot. Imagine we now have a different light source. Before, this was sort of perfect or near ideal illumination in a controlled environment. Now the illumination really doesn't look that great, and this has severe impact on our histogram. We see we don't really have this peak at the end anymore, but we only have this big peak here, and it's really spread out. And if I take pixels in the range from before, which was somewhere here or so, I think, this would visualize not all the pixels in here because they don't have the intensity anymore. Plus, it would visualize also some of the outer areas just because we had a lack of illumination there. So if you see, if we try to use these thresholds from before, we really don't get anything useful because here we're just building segments, and these segments, they would be processed further, say for object recognition. But if I have a segment like this or that, I don't think this is any useful shape or anything useful that could be processed very well. So we see this histogram approach for segmentation is helpful, but only if there is little noise and if we have reliable illumination. Here, for this setting, it doesn't really work. Then there are lots of other approaches for segmentation. I mentioned before, some algorithms, they do merging, some they do splitting. This could even be combined as a method that is called a quadtree. A quadtree is an approach that allows us to do um, a decomposition onto an image. And there's a question here: are there specific use cases where the segmentation by histogram could be used? Yes, for example, if you need high speed, you don't want to buy expensive hardware, then this would work well. And if you maybe have a controlled environment, controlled illumination, little noise, then such an approach could be your choice because it runs super fast and you can set the thresholds. You don't need an expensive learning system with expensive hardware. This would be your choice. For a setting in the wild, so in the wild just means outside or randomly, you would maybe have something like that, then maybe the segmentation approach isn't too great. But even when you have a illumination setting like this, also other more sophisticated approaches like a neural network, they would struggle severely because you just have too bad illumination, and even a neural network would hardly be able to filter this out well unless you have a lot of training data with a lot of data augmentation. Um, but for a setting like here, without the noise, with proper illumination, go ahead using the histogram. And this quadtree is a combination of merging and splitting. And what it tries to do is it will start the segmentation process by splitting the big image into multiple regions. And then it tries to split these regions further. And once you stop splitting, it will actually merge everything that has sort of fulfilled this neighborhood criteria or your uniformity criterion. So a quadtree combines this, and there are lots of variations of a quadtree, in fact. So it's a combination of splitting and merging. But now we'll actually come to a learning approach. And we will first start with this machine learning algorithm in general, and then we will apply it to an image problem. Who of you feels familiar with the k-means clustering algorithm? Thumbs up. If you have not come across this, thumbs down, because and I would be happy if someone is brave enough also to send a thumbs down if he or she does not know it, because we have a lot of other students here, not just from AI. So I'll say a few words first about k-means. And then we look at an example, and this is a very generic machine learning algorithm for clustering. First of all, has nothing to do with vision, but will apply to vision in a moment. So, in machine learning, we have three directions, three pillars of algorithms: supervised, unsupervised, and reinforcement. And k-means is a so-called unsupervised algorithm. So our observations, they don't have labels. We just have observations and we want to find a hidden structure among our observations or examples. Whereas if you have, say, classification, that would be a supervised problem because we have observations and we want to put them into different classes. So, and in k-means, so from my notation here is we have these observations or examples, we call them X. And X can be something, can be a pixel, as we will see later. It could be something totally different. Say, it could be a machine. Say, we have lots of machines, say, stretch blow molders that create PET bottles, and we want to find out if there were any issues in the manufacturing. And we could try to build a cluster of the proper ones as well as the malfunctioning ones. So this could be any kind of observation, not necessarily just pixels. could be a complex data example. And X is in bold because it's typically not just a scalar value, but something like a vector, for example, where we have multiple values in it. And I have m many of them. So my notation is we have m many examples, and an example has n many entries. If you look into other literature, sometimes n describes the number of observations and some other variable, the number of elements in an observation, but I say m many observations and n like Naples are the number of entries in one example. And this example has an index for which I use an upper index, so a superscript I to count. And now I want to cluster I want to partition these m many observations into k clusters. And k must be less than or equal to the number of observations. Because if I have 10 observations, I can cluster them in 5 clusters, in 10 clusters, but not in 20 clusters. That doesn't work. So k must be less than or equal to m. And each cluster has a centroid or mean, and that mean it would be denoted with this mu, and it also has an index. For example, just J, it's just a different index than the observations. And the mean would be sort of the centroid of the cluster. We'll see in a moment how that could be calculated. And now I want to run this algorithm, and I want to assign these observations to the cluster. When I run the algorithm, I need to define how many clusters I want. So the algorithm needs to know how many clusters I want. And then it will try to build these clusters and assign these observations to the correct cluster, or the nearest cluster center. I need to start, when I run the algorithm, I need to put the centers of the cluster somewhere. And that's why this is often done randomly. So this algorithm is non-deterministic. So if I run it again, I may get a different result simply because I put the cluster centroids somewhere in the data set initially. We'll look at an example soon, but I'll first briefly show you what in pseudocode, what k-means does. So k-means k is the number of clusters, and I randomly initialize these cluster centroids. So I have mu1, mu2 up to mu k, and for now we just say we deal with real values, and each mu1 up to mu k is a vector of n many real numbers. And because this is random, this makes the algorithm non-deterministic. And then I have an outer loop, and the outer loop keeps running for very long until we stop reassigning examples or observations to a new cluster. So once we run this outer loop once more, and inside we don't change any assignments of the examples to a cluster, then it's converged and we stop. And then within this outer loop, I have 2 inner loops. The first inner loop, what it does is it calculates an assignment of the closest cluster, or the cluster closest to my example. So I go through all my m examples. Index I, remember, is this one here for the observations. I go through all the examples and I simply check. I have these random centroids at the moment. Which cluster center is the closest to my current observation? And I assign this, say, to cluster 5. Then the next one to cluster 7, whatever. I just check which one is the nearest one. The nearest calculation could be done through some Euclidean distance. We could use some cosine distance. There are lots of different measures that we could use for distance. But for now, we just say we use Euclidean distance. And then each example was assigned to a cluster. And now I go through all my K clusters, so from 1 to K, where I reassign or where I recalculate the center of the cluster. So I go through all the points, so all the observations that were assigned to my cluster, and I calculate the mean. And that's the new center of the cluster. Because these centers have moved now, I need to run this loop again in the next iteration of the outer loop because some observations may now be closer to a different mean. And I keep doing this, and once I don't reassign anything anymore, I'm done. So this is a very simple algorithm, in fact, and we'll look at an example what this looks like now. So we have these observations here, and we have the observations in gray. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I have these centers, red, green, and blue. And now I assign each of the observations to the closest center. So this observation gets assigned to red, all of these here to green, and all of these to blue. Now I have done the first inner loop. I have assigned each example to a cluster. Now I need to do the next inner loop where I recalculate the mean. For this cluster here, it's easy. I only have one observation, so the center, the mean is not this one, but the mean actually becomes that single example. Then for all these green ones, I calculate the mean, which moves slightly, as we can see here, as well as for the blue one, the mean moves a little bit. Now I repeat this because what I see is this is the center of the red cluster. And there's already one observation there, but these two observations, they are also closer to the red center than to the green center. So I do this again, and then I recalculate the means again. And when this algorithm converges, I have this solution here. And remember, it's all non-deterministic because it's subject to where I put these clusters initially. I could spread them somewhere else when I initialize, and then I may get a somewhat different result. So it's non-deterministic. Do you all feel okay with k-means now? Maybe just confirm whether it looks okay to you. We will see in a moment what this can be used for in image processing. Don't worry, because so far this is just general data. And here it's 2D data. The observations are 2D, but this also works in higher dimensions. That's why we say it's n-dimensional data. And there are lots of different clustering algorithms. Imagine we have this data here. So these colors are initially just for illustration. So this is sort of some Mickey Mouse data set. These colors, they are just for information. They are not calculated yet. But what we see when we look naively on this data, we see there is sort of a cluster here, there's a cluster there, as well as a big cluster here. Plus, we have these outliers. They're visualized in yellow because they're just so far off from the clusters. But there's no clustering run yet. It's just for illustrative purposes. Now, if I run my k-means algorithm, and I say I want 3 clusters because I need to define the number of clusters, then what k-means could deliver is, for example, this. This is my blue center. I have a green center here and a red center, and I have these points assigned in the color to the center. I just got a good question. What happens if all the centroids are randomly placed in nearby locations in this example? Well, if they're in nearby locations, it will still converge eventually. It may take a little bit, but there actually the k-means converges quite quickly. It would just take a little bit longer, but not much longer, in fact. If these centroids were placed very close to each other, it would still converge relatively quickly. And since it's random numbers, real numbers, we assume that the centroids are not exactly the same location. And since it's real numbers, this is quite unrealistic. But even if they're close, it will converge quite quickly. And if we run the k-means algorithm on this data set, we would get this. But k-means, k-means, what it always assumes is I want um, I want a circular shape. So in 2D it would be circular, in 3D it would be a sphere, in 4D it would be a hypersphere or something like this. So when we use k-means, also with this Euclidean measure, or Euclidean distance, I would always get these spheres or circles, and that's why this algorithm would not really, for this data set, be able to break or really cut off this ear and this ear from the face or the head, but the pixels around at the edge of the face would typically still belong to one of the ears. So this would be a quite common outcome when you run k-means here. There is an algorithm that is called EM clustering. So EM clustering is eventually an application of something that we call expectation maximization. Any one of you has heard about expectation maximization? If so, maybe thumbs up or thumbs down. Expectation maximization. We will see a little bit about expectation maximization a couple of weeks in this course, I think, when we look also in the Kalman filter. So expectation maximization is a very generic approach to fitting parameters in a complex statistical model. And EM can be also applied to clustering. And in fact, EM clustering is just a generalization of k-means. So the first phase would be the expectation phase. The second phase would be the maximization phase. But it uses far more complex statistics than we use in k-means. So we could argue k-means is just a special case of EM. And this EM algorithm, when you apply it to clustering, it would not find you circles, but it would find you a sort of elliptical shape. And with these elliptical shapes applied here, when we have Euclidean distances, we would actually get our two ears and our face quite well. But we as humans, we need to define, or we as the user need to define how many clusters we want. Do you think what would happen if I say I want 4 clusters? Could you guess what we would get out of here if you say I want 4 clusters? Do you think the result would look reasonable or not? I'll see. You can turn on your mic or you can share this here in the chat. What happens if I have 4 clusters?
They won't have very good distinctions because we can see there are three clusters which are distinct. But if we introduce a new one, then it would get messy. Maybe the blue one would be divided in half, or some of the red one would be taken over.
Exactly. Blue one could be divided in half and part of the red one or the green one. It really would not look nice. And this is one of the challenges of these classes of clustering algorithms. You need to define K. So there are other clustering algorithms, for example, hierarchical clustering algorithms. They could try to optimize and find you a good K. But here with these algorithms, we need to define K. And there was a question also because about this random initialization. If you apply like k-means or EM clustering to a data set, you would maybe look at the result, check if it sort of makes sense, and if it's really off from what you would expect or want, you would just rerun it. So it could happen that you may have to run this a few times until you get a proper solution, but that's a non-deterministic algorithm. Um, and the shapes for k-means is circular for um, and there was a question here if there are approaches to automatically set K. As I said, for example, hierarchical clustering, which are again totally different approaches. Um, there are some approaches you could, for example, try out multiple Ks, and you would pick then the K for which the error has dropped the most in between. Say the error would be you would have sort of a ground truth, and know where each observation fits. And when you say you increase from 2 to 3K or 2 to 3 clusters, then from 3 to 4, the error would drop, and you would sort of maybe take the K for which the error has dropped the most with respect to the previous K. The lowest error would obviously be if K is the number of observations, but if you have 1,000 observations, you don't want 1,000 clusters. So just arbitrarily increasing K means the error will shrink and shrink, but you would do the cutoff there where the error has maybe dropped the most. And that would be typically a very small number of Ks rather than a very big K. So that could be one approach that is sometimes done. So I hope this answered the question here in the chat. Yeah, and now you're wondering, why are we discussing all of this in a computer vision course? Because we can use it for a very interesting segmentation problem, and we can use it, in fact, for image compression. So here are a few more things, but I have said already all of this here, how to pick K. We'll skip this example. And now we can apply k-means to reducing the size of an image. We'll look into the code later, what we are doing. So I'll show you the example first. So we have this original image. And this image has 615,000 unique colors. Maybe not anymore in this PDF because there is some compression, but we'll look into the image in a moment and see where it comes from in the code. So this photo was taken somewhere in Southeast Asia. 96,615 unique colors. Now, how do you store such an image? What we obviously could do is, but that's the very inefficient way, is as we discussed so far color images, we said we could store an R, a G, and a B value per pixel. But that could be then 3 bytes per pixel. And if you have a lot of pixels, you need a lot of bytes. So it's super inefficient. The next thing we would do is a color map. A color map would allow us that I have a certain number of unique colors in here. And for each unique color, I store R, G, and B. And I store this in a map. And for each pixel, I only store an index where to look in the map. So I don't store in each pixel exactly the R, G, and B value, but only an index to the map. And in the map, I store once per unique color the R, G, and B value. Maybe just confirm if this makes sense to you. Now we can think about, still, if I have a lot of unique colors, say a lot of different ones, then this map becomes really big because in the map I need to store an R, G, and B value per unique color. Now my goal could be, I want to reduce this image size by applying a segmentation approach, concretely k-means, so I can reduce the number of unique colors, so reduce the size of the color map a lot by taking advantage of how certain pixels belong together. Obviously, a very, very inefficient way could be, say, for segment, like a very, very inefficient image compression could be, I say I only want 100 unique colors, and I just take the spectrum of possible colors and I try to split that spectrum into like 100 regions. And then every pixel in that region, I sort of want to, or we can say, no, we can say maybe, let's say 1,000 ones. Say, I want to split the R channel into 10 intervals, then the Chi channel into 10 intervals, and the B channel into 10 intervals, which are all just the same. So I split the 256 possible ones into 10 intervals or into 8 or whatever, but let's say 10. That means I would then have, say, if I pick 10 times 10 times 10, I have 1,000 unique colors. And everything that fits into this specific range or interval, I would just map to, for example, the center of that interval or the mean or whatever. Have you understood what I have proposed? Maybe just confirm if this got clear or not. Okay, seems to be clear. But splitting it this way, do you think that's a smart way to split it this way? If you think it's smart, maybe thumbs up. If you think it's not smart, thumbs down. And if you have any criticism of that approach, turn on your mic and or let us know in the comments if that sort of splitting scheme would be actually smart or not. I haven't seen any thumbs up or thumbs down, so you can just assess if my scheme really makes sense or not. And I'm telling you, it does not make sense because I can do it that way, but I'm just splitting the spectrum into certain areas, but maybe a lot of my pixels are just for a certain small number of the groups in the spectrum. That means the pixels that really matter, they would lose a lot of their color, while in other areas, maybe I don't really have a lot of pixels from that scheme. So that doesn't make much sense. So I rather want to say I want 1,000 unique colors, but I want a machine learning algorithm to figure out which of those 1,000 unique colors are really the important ones and try to find them in a way that the error gets quite low. So the error is always per pixel mapping to one of these, say, 100 or 1,000 unique colors that I want. So this difference getting from my pixel color to the nearest unique one that I still retain, that error should go low. And so I somehow need to define or find out which are these, say, 1,000 unique colors that make most sense so that the mapping from each pixel to the closest unique one has a low error. Maybe confirm if you got that proposal. Good. But now the question is, how do I find these 1,000 unique colors that keep the overall error low? And for this, I can use k-means. We'll look at the code in a moment. But let's see this. Actually, so we had these 96,615 unique colors. And with k-means, I just compressed this to 64. So even not 1,000, so 64. So the color map will shrink a lot. And you see, the error is quite low, right? Doesn't look that different. So this is the original. This is the result. You can see some changes in the background and the color up here, but Are you impressed that I can still visualize this image so well just with 64 unique colors? If this, and if you are, send some more reactions or turn on your mic, and some of you have said, we can play this game further. Obviously, what I've just shown you is the nice one. I could also just pick randomly 64 colors, just randomly, and say each color gets mapped to, so I pick 64 colors randomly, and each pixel will just be mapped to the closest color that I picked randomly. This one really looks worse. So the one before, 64 colors with k-means, looks really good. 64 randomly chosen, we see quite a loss of information. I can play this further. I can just say 10 colors randomly picked with k-mean. Not randomly, sorry, 10 colors picked with k-means. Obviously, 10 colors is quite limited, but for 10 colors, I think this still looks quite good. What we see is the background obviously is a problem compared to the original one. But for 10, given that it's learned by a machine learning algorithm which colors to keep, not that bad. If I change it to 5, I get something like this. And if I change it to 2, I get a binarization. But even the binarization looks quite reasonable and a 5 because it filters out all this background stuff and just keeps the front stuff. So not too bad, actually, purely based on machine learning. I got a question here what the algorithm does exactly. And is what we will answer now. And there's a question about the centroids. For the centroids, it's not the um, X, Y, and Z. It's the R, G, and B. But we'll look into the code now, and then it will become more clear. So there's a machine learning library that many of you have probably seen, scikit-learn, very famous machine learning library, offers a clustering package, and in there is k-means. And we also need to load a sample image, and the sample image is the one we have just seen, china.jpg, comes with scikit-learn. We can load the image. We can say, I want 64 colors. I want to compress the image. We'll see in a moment how this works. And then we will plot the image. And for plotting, all we do is we use matplotlib. We put the image there with a title and something. Now, the interesting one is the compress image. It's a helper function. And I pass an image. So the image is passed and the number of colors. What it first does is it converts the image to a NumPy array and normalizes the values. So values are between 0 and 1. And then it does a sort of lengthy conversion back and forth because we have this image and it needs to be put into a shape so we can put it into k-means. So some of this code here is not too interesting for now, and it also has a small helper to speed up a little bit. But what matters is I have my image, and the original image just needs to be reshaped so that it's in a structure that scikit-learn can work with it. I'm not explaining this in detail. Feel free to look it up or run it in a debugger if you wish. But what I need is the image needs to be converted into a format so I can run it in k-means. And then the number of clusters is the number of colors. And then I train the model and then I predict. Predict means I apply the clustering to every entry in the image array. So so each pixel gets eventually assigned to the unique color, while this one here finds me the optimal or near optimal unique colors. And since here I had reshaped this image into a format so scikit-learn can work with it, I need to convert it back and recreate it so that I have an image that can actually be visualized, and recreate image eventually just undoes this and applies the right centroid to each pixel. So recreate image does this, but it really doesn't matter what it does exactly. It's just crunching the data that it's in the right format, but feel free to run it in a debugger in case you're curious, and then we visualize it. The important one is here. We have the image, the number of colors is the number of clusters. And when you look at the data format, what it does is it's the RGB values, and it tries to find the optimal centers for those 64 or 10 unique colors, so that the overall error of mapping a pixel to the unique color goes down. So you see, you can use machine learning for this image processing problem. And what we are doing here, in fact, is just some kind of segmentation, because we are segmenting the image in a way so we get a number of unique colors while trying to preserve the image as much as possible. When I saw this the first time many years ago, I was quite impressed how well this image still looks with 64 unique colors that k-means found compared to the randomly found ones. If you feel that this is quite an interesting application of k-means for image segmentation, let us know. And if you're curious to run it, you'll find this example is from the scikit-learn library documentation. So you just find the exact example on the internet and the data. Feel free to run this on other images, on a different number of clusters, whatever. But it's great. It's a really cool example of how we can use clustering to very efficiently compress an image. Now we have finished regions of images and segmentation, and we can. And there's a question why we divided our values by 255 up front. That's just a detail. So the values are between 0 and 1. It could maybe just help to have this. Well, the format should be fine, but probably this would help also with the kind of data that k-means is expecting. But again, probably also without the 255, it would run. Maybe the k-means could run a little bit faster if I have this normalization. Just run it and see if you leave it out, if it still works. I don't think it will. Maybe the reshaping would expect that we are in this range, but I don't think so. Just give a try and see if it still works. But it's probably just a detail. And that's why I said some of the details here, they don't matter too much to me for now. It's simply an example of how we can apply the k-means. And there are a couple of more nasty things like recreating the image. But you should just see this as given, and feel free to study it, but or not. So we have finished regions of images and segmentation. And then we'll come to the second chapter for today, feature detection. We will look into 3 feature detectors. And why do we do this? So we have seen in the lecture last week how to find simple features like edges. Edges was the beginning, so we saw some operators last week. And in a lot of object recognition tasks, you need features in an image. And these features are then used in some machine learning algorithm or in some rule-based system to infer about objects in an image. So we need to pre-process the image to get features. These features could be edges, they could be corners. We will see corners today, for example. But they can be other stuff like straight lines as well, which is the Hough transform. And those properties can then be used in an object recognition algorithm, because a lot of machine learning algorithms, they don't run very well on raw data. And because raw data is noisy, messy, you have a lot of artifacts in it. So often you want features and then work on the features. And we'll see next week what these features are useful for. Convolutional neural networks and transformers, they are a totally different approach. They would learn features on their own from the raw data. But computer vision today is not just convolutional neural networks and transformers because they come with a massive need of computational resources, and they still have some other downsides, by the way. And for other problems, you need different models. And for these other models, you still need features. That's why we do feature detection today. And sometimes you would even pre-compute features and feed them into a neural network for specific tasks. While neural networks are great to learn certain features on their own, some of them are helpful, but there are also other approaches. So sometimes you need to make some compromise or combine certain methods. And that's why we're doing feature detection today. And next week, we'll see how to use these features as well as how to learn features on our own with a, for example, convolutional neural network, or in a couple of weeks when we see selected topics, we look into vision transformers. And so what is actually a feature? Because I've mentioned this term a few times. We've seen it a few times in this lecture. So a feature is an interesting part of an image. So what is interesting? Something that is distinctive, that can help us later to detect some object. For example, a corner or a straight line or something. And features, usually we speak about local features. As I said, they are associated with certain object features, maybe some part of an object, some corner of an object. And oftentimes, based on the feature detector, there are a lot of features in an image. And we can calculate them relatively quickly, and a lot of them. And then later, maybe in some rule-based system or a learning algorithm, we only pick the features that are actually relevant. But we can efficiently calculate a lot of features and then see how we use them. And we could also think about global features, but often local features. So local features, straight lines, edges, corners, they help us to generalize later for the scene representation. I've mentioned edges, corners, there are also straight lines. We've seen edges last week. Today we see mainly lines and corners. There are also blobs, reaches, and lots of other features. And features can be used, obviously, for object detection, can be used for object tracking, classification, image matching, whatever. So lots of possible tasks. But calculating these features in a repeatable and accurate way can be tricky. For example, we want our features to be invariant to translation. So translation means I have an object in an image, say it's in the center of an image, and now if I move this object within the image, say to the upper right, I still want to find these features if I apply my algorithm. So if I apply the algorithm to the first image where the object is in the center, I want to find these features in the center. When I move the object to the upper right or somewhere else, I still want to find the features then in the upper right. I don't want to find different features or no features. But it's often not that easy because these feature detectors, they make a lot of assumptions. I also want this to be invariant to rotation. So invariant means not affected by translation. Rotation means I have my objects and they are rotated in the image. I still want to find them, say I rotate them by 10 degrees or something. I still want to find the features. Scale means how big the objects are. If the objects are very big or very small, I still want to find the same features. And ideally, I want my features to be robust to lighting variations, noise, blur, quantization. So a lot of factors we have seen, especially illumination, noise, blur, a lot of other things that could affect us how we take the photo. And even if lighting changes or there's some noise, I still want to find the same features. It turns out that the features detectors we look today at, they're not invariant to all of this. Some feature detectors are invariant to some of that, while they are more affected by other of these sources, and other feature detectors are invariant to other challenges. A neural network learns features and then uses them for some downstream task. Like a convolutional neural network is invariant to translation and a little bit of rotation. But a neural network is not invariant, or convolutional neural network is not invariant to scale, for example. And the other detectors we study today, before we look into neural networks next week, we will discuss today which invariance they have as well. Now, welcome back from the break. Before we continue with computer vision, I want to quickly share something with you. So we see that policymakers are more and more interested in AI. So politicians, they try to regulate AI, and there's now the AI Act in the European Union for the last 2 years that you need to comply with when you build AI systems. So later, when you work in industry, you need to be thinking also about regulatory requirements for the kind of stuff you're building, so they are safe and compliant. And there's now the AI Act. The AI Act itself, something that I've been quite critical about, but that's something I discuss in my innovation management for AI lecture, which you will take next semester in parallel to your internship. But currently, the German government is thinking about how to enforce the AI Act. So, which market surveillance agency would be in charge of the AI Act, and how could actually these European laws be enforced? And the German parliament proposed a law about this, and they are currently debating it. And as part of that discussion, there was a hearing in the German federal parliament in Berlin on Monday. And I was invited there as one of the expert witnesses. So we were like 10 expert witnesses who commented on that law, how the AI Act would be enforced, and also discussed alternatives. We were asked questions by the members of parliament, and I will share. So that's where I'm sitting and talking about the proposed law and discuss that with the members of parliament. This is in German, obviously, not in English, but I'll share the link with all of you here in the chat in case you want to follow this. We also wrote written evidence. I also wrote the written evidence here for the parliament. So this is something you could easily machine translate. And maybe you can take a look at this summary here, as well as the recording of the video. So I do this from time to time. I think this was my fourth time in a hearing in the German parliament, but I've done similar work also in the European Parliament and some other parliaments. I'll share the link with you because once you graduate and you build AI systems in industry, they need to be compliant, and you need to think about compliance. So I've just shared the link here in case you're curious about all of this. We will talk more also about laws around AI and regulation in the innovation management course, which is one of these courses in parallel to your internship. So you'll see more next semester. But just in case you want to watch the hearing from Monday, go ahead. So back to feature detection, and if we have this sample image here, there are lots of objects that could be characterized by the presence of straight lines. Say we want straight lines, we could find quite a few straight lines in here. These straight lines are typically purely natural, or they are purely artificial, because in the natural world we hardly have a lot of really long straight lines. but it's here what humans have built. And these straight lines, they could be helpful for object detection. They could be helpful for the autonomous car, so it knows where to drive and all of this. So feel free to also look at these additional resources where this data comes from. And today we will look into different approaches how we can identify straight lines. Maybe you're wondering, why are we not just running edge detection? Edge detection is something we did last week. And with edge detection, we get edges, but these edges are not necessarily straight. So edge detection could be an early step, so we get edges, and then we try to find straight lines by using some of this edge information. But edges are messy, they are not continuous, some pieces are missing. So edges are just a beginning, and straight lines are for certain problems more helpful than just using edges. And there are lots of different feature detectors. We could spend the whole semester just on feature detectors, but I'm covering today 3 of them that are overall helpful, in addition to the edge detection we have done last week. And then I think you have a solid foundation and you know how to detect features. And then when we see neural networks and transformers, they are even able to self-learn some types of features. So we have a good portfolio then of what is actually possible. Now, in feature detection, often we also see so-called voting algorithms because oftentimes it's not feasible to check all combinations of features by fitting a model to each possible subset, but rather with voting, we try out some of them. It's a more general technique, and we let features vote for all the models that they are compatible with. So we can go through the features, we cast votes for model parameters, and then look for model parameters that received a lot of votes. And with voting, we can also address, for example, noise and clutter features. But those would typically lead only to little votes, and we can actually, with voting, filter out the relevant or somewhat good features. And there are 3 algorithms today. 2 of them do a lot of voting that we will look at. And one is a very, very generic one. It's called RANSAC. And RANSAC, in fact, is a highly generic feature estimation or parameter estimation algorithm that can be used in vision, but can be used for lots of other parameters as well, not just in vision. So we briefly look at it, apply it to vision, and then we see 2 more vision-specific feature detectors. So RANSAC is an iterative algorithm, and RANSAC stands for Random Sample Consensus. What it does is we randomly select a so-called seed group of points on which we want to base the transformation estimate. We will later see this for one type of feature. Concretely, we will see this for a straight line, but this can be generalized and can be applied to lots of other parameter estimation as well, even far outside from vision. Then we want to compute the transformation that we are looking for from that seed group. We find all the inliers from our data set that fit to this transformation. And if the number of inliers is sufficiently large, then we could recompute the estimation of the transformation on all the inliers. And we only keep the transformation with the largest number of inliers. Then probably you want to know, how does it work? And I think for that an example is great, because we keep repeating this until we have the transformation that actually got the most votes. And we can look at that from an example. So what you see is we have a data set, and the data set is here, which are all the circles plus the 2 squares. But we have this seed group among the data set, which are these red squares. And here we have the circles as well, and we pick two other seed group or two other elements for the seed. And so these are two subsets, and we see now how RANSAC works. What we want to find is a straight line in this data set. And we have now picked randomly this seed group. We can apply, we can then pick them and say, well, we put a straight line through this seed group. And then we see how many points are somewhat close to that transformation, so the inliers, because there's noise. They don't need to be perfectly on the straight line, but at least in some corridor. And maybe we find these other two where we could agree they are still somewhat within the corridor, assuming there's some noise. And this corridor has a certain parameter that we could call T for its width. But we see here really, this didn't really lead to much because we largely have outliers, not many inliers. And then we just repeat the loop and we just start from scratch and say, well, here the transformation didn't really work. Let's try again. Then we randomly pick these 2 points here. We put the transformation in and we see there are a lot of inliers. So we have a lot of voting here, and the voting comes from each of these examples. They vote that they would fit to that transformation. While here, for the first transformation that we tried on the seed group, we did not get many votes. Here we got a lot of votes, and we could say, well, we are fine, or maybe we still hope for something better. But here we largely have inliers and not many outliers. So that's the concept of RANSAC applied to finding a straight line, and this also visualizes the concept of voting. But RANSAC is highly generic, could be applied to far more than just computer vision. Now, what is RANSAC helpful for? So it's a generic method for fitting models. It's actually quite easy to be implemented, and we can easily calculate the failure rate. It is generic, but it can only handle quite a moderate percent of outliers without the costs getting out of control. And many real-world problems, especially the ones that have a lot of noise, they have a high rate of outliers. So the RANSAC is cool, but we would probably need to try a lot of different seed groups until we ever get close to something. And if this data set is not just like, like 10 examples or something, but a lot more, like thousands or millions of examples, then this wouldn't really work. Because what we see here, these points, they could be, for example, edges found from an edge detector. But if I apply an edge detector, as you saw last week on a bigger image, we get a lot of potential candidates. And then applying the RANSAC here is probably quite inefficient. And how would you know you have found the most optimal one? At some point, you would probably just abort if you say, I have this percent of inliers and I'm done. Because it's an optimization algorithm. You don't want to try out all the combinations because that wouldn't work in a feasible amount of time. And you would pick a threshold. And then if you don't reach that threshold, then you would have not your good enough line. So I hope this addresses the question that was sent in the chat. But RANSAC is generic, yet for probably the line detection could be done, but not too great. We can pick a different approach, the Hough transform, which is purely made for finding straight lines in images. So it's not generic at all. And it turns out the Hough transform is a voting algorithm too, and it can handle a very high percentage of outliers. Even if the vast majority of examples are outliers, the Hough transform will probably still find a reasonable straight line. And it's purely made for this problem. So there's a lot of text here, and I'll just tell you in essence, and then we look at an example. So the Hough transform is a really good feature extraction technique used a lot in image analysis, computer vision, digital image processing to find straight lines. It applies some voting and it transforms the data into a different space where it turns out that we can do this voting quite easily. The original Hough transform addressed purely straight lines, and over the years, extensions have been proposed in the literature. For example, the ones for circles or other types of shapes. But we'll look at the classic Hough transform. So if we have this image here, what we could do is first we do edge detection, and then we get this one here, and we would eventually put in some candidates of straight lines. You're wondering probably, what does this one look like and this one? It looks like hair, but I'm telling you, it's certainly not hair. It's a different space to which our data will get converted. And in that space, we can do our voting. But we'll see that space soon and we will visualize it. So we would see potential straight lines, and eventually this could be an outcome of the Hough transform. It has found multiple straight lines, but because of noise, maybe not all of them are perfectly completed. We also have quite some shade in the image, by the way. And maybe we would have to fine-tune the Hough transform a little bit. But this is what the Hough transform would return us, and for this data set, and possibly it's already quite okay. I get a few straight lines, not all of them. Also has to do with illumination, with scale and rotation and all of this. But we find some straight lines, and we certainly get more out of it than from the edge detector. This one here is, for example, the Sobel operator or the Kenny edge detector that we discussed last week. Now, how can I get from this image to that one? First step is edge detection, which we did last week. And now we'll see how to get from the edge detection to the result. I have to tell you, when I studied computer vision as a student and the Hough transform was explained, I really struggled to understand what that professor wanted. He was a very good person, but I didn't get too much out of that lecture. What I like are examples. And since this is a big computer vision course, we look into lots of topics. And finally, there's also enough time for your projects. I will not discuss every little detail of the Hough transform with you, but rather show you how it works based on an example. We'll look into the transformations. And then if you find this interesting and you want to investigate it further, maybe someone may pick this as a project. Every year, probably someone picks the Hough transform. Obviously, now we have a lot of students in this class. I don't want that all of you suddenly pick the Hough transform. I would anyway be happy if we can fill the 40 groups of 2 to 3 students, first of all, for the Cronus challenge in 2 weeks, because Cronus spends a lot of time and resources on the challenge. So I would be very happy if 40 groups actually do this. But there will be more than 40 groups because 200 students signed up for this course this year. So I'll show you this example. We have an image of an apple. We apply edge detection, and we get, obviously, this is just an illustration, but so we can still follow it. We get these points from an edge detector in red. What do you think when I want my straight line? Are most of these edges on the straight line or not on the straight line? If you assess this image, maybe let us know in the chat if you think these red edges we have found, are most of them on the straight line or not? So there's a majority for not. Yeah, because there's these few here, a little bit around the apple, but most is really off. And we see there are artificial edges as well because this apple has some shade. which creates artificial edges that don't actually exist, but there's a change of illumination, so noise as well. Now, there will be quite a few tough transformations in here. But you've seen all the math before. Imagine we take the first point of the edge, the first one we found. And I need to convert this one now into, I need to put a straight line into that first edge. So I'm not trying to find the straight line yet. The straight line, the result is obviously behind the apple, but we need to make it there. So I want to put a straight line into the first edge, which would be this green one. Then I put another straight line with a different angle, the blue one, into this edge, and so forth. And for each of these lines I have put in, I can determine what's the distance to the center, which is here, this R1 or R2. So I assume I have a right angle. And what's the distance from the center? I have R1 for the blue line, R2 for the green line, plus I have these corresponding angles. So I have theta 1, which is the angle between this line here and the blue one to get to the center. And I have theta 2 corresponding for the green one with R2. Are you all with me up to here at the moment? It's just basic geometry. Maybe thumbs up or thumbs down. So, and I'm doing this only for the first point of the edge at the moment. I'm putting a lot of different straight lines. And for each line, I have an R and a theta. Now I want to represent the green line and the blue line as a point in R theta space. So I have a new plot here, which is in R theta space. And for my blue line, I have the R1 and the corresponding theta. And then I would put the blue line, say, in here. I have that R and so that R and that theta. For the green one, I also have an R and a theta, which I put in here. So I'm mapping the straight line as a point or to a point in R theta space. And I'm doing this now with a lot of different straight lines that I put through the first edge. And for each straight line, I calculate R and theta and put it into R theta space. So what I get is a lot of points in R theta, and eventually this looks like a sine, this function. So this sine function in R theta space through all these points would describe all possible straight lines that go through my first edge. Maybe confirm if you're still with me, because it's a few tough transformations that we're doing now. But okay, looks okay from the answers. So I have this sine curve, and this curve represents simply all the possible straight lines going through the first edge. Now, so this is my sine, so just from before, I do an interpolation for this first edge. Now, what I have done for the first edge, I am redoing for the second edge. For every edge in here, I put in all the possible straight lines. So I put all the possible straight lines here, there, down here. And for each point, I would get a new sine curve or some other curve, probably sine curve in R theta space. And that's where I'm here now. So it's not always or just part of a sine. So we see each of these sines or each of these functions in R theta space, so this one here, this describes all the possible straight lines through one specific edge. So you see what I have here are all the possible straight lines through all edges. And this kind of visualization is the one we already saw here, like these hairs, but it wasn't hairs, I told you. I told you it's a transformation. So what I have here is this one curve would be all the straight lines through one of the edges here, for example, maybe this one or that one or whatever. And now I'm coming to the voting because I can do a voting, and voting would mean where do all of these curves in r theta space intersect? I have one intersection here. I have one intersection there. I have a few intersections somewhere here. And I see I have most intersections in r theta space somewhere here, precisely here. And in that point, I have most of the intersections. So I'm doing the voting, and voting is simply counting all the intersections. And here I have the most. Now I'm asking you, what is that one point in r theta space representing? There's one point in r theta space. What would such a point be in the original image? If you feel you know the answer, maybe thumbs up, and I'll wait for you in the chat, or you turn on your mic. Or if you feel you don't know what that one point could be in the original image, maybe thumbs down. And some more answers would be great. So we got some thumbs up. For those of you who sent a thumbs up, maybe send us in the chat then what you think this could be. Or turn on your mic and tell us what you think that one point would be in the original image. I'll just wait a moment. So it matches with most edges, yes. So it matches with most edges. And that would be exactly the straight line behind the apple. So you got that correct. So first of all, it's a line. That's what you wrote in that chat. That's the first thing. Because a point in r theta space is a straight line in the original image. And the one it is actually one, it matches with most edges possible. And that would be our straight line behind the apple. So you got that right. So I know it's a complex transformation. That's why we do it again. So we have the image, we apply an edge detector, and then we put a straight line through the first edge, put it in r theta space, the next straight line through the first edge. We get all these points in r theta space. We have this sine curve, and that sine curve describes all the possible straight lines through the first edge. We do that for all the edges, and we see where we get the most intersections in r theta. And that one intersection is a point in r theta, which is a straight line in the original image. And it turns out that's the one, that's the straight line we actually were looking for. So this is the Hough transform, an algorithm purely made for finding a straight line. We can collect a little bit in the chat what you think could be some downsides. First of all, you can just comment in the chat what you think is positive about the Hough transform and what's negative about the Hough transform, because it comes with some downsides too. I'll let you collect a little bit in the chat, and then I'll tell you in a moment what I think about the Hough transform. Meanwhile, I will tell you a little bit about my experience with the Hough transform. When I studied computer vision in my studies, so there was a computer vision course I had in my bachelor's, but also one in my master's, and I did the master's at Imperial College. The professor was very picky with it because there was a big coursework problem, and it counted towards the final mark of the course, where we had to implement the Hough transform in code and run it on some sample data. Plus, we had to write a big report and step by step write down how eventually that straight line got computed. So it was, I think, dozens of pages in my report, lots of math, but contributed towards the mark, and I got a very, very good mark. So in England, the marks are between 0 to 100, where everything, so 0 is the worst, 100 is the top, and 70 is sort of A plus, whatever, so the 1.0 in Germany. And everything over 70 is difficult, and I got way more than 70 in that course. So, but also because of that coursework, and enjoyed it a lot. But implementing it from scratch took me quite a little bit of time and make it work. And we got some comments here in the chat. One person says the result would be pretty precise. Yes, it works even if there's a lot of noise. It works surprisingly well because even if most of the edges are noise, it can filter it out, as we've seen here. And the negative thing is like scaling this. Yes, so running time is a challenge because we need to do some discretization, and the smaller we discretize, the longer it takes. So high memory cost, yes, very robust, but extremely slow and resource hungry. So there are again, and one benefit is, yes, it also detects incomplete shapes, absolutely. So it works extremely well, but running time is an issue. So there are again lots of proposals how to speed it up, make some compromise, how to apply this scheme to different shapes, like circles or whatever. So there are a lot of different Hough transforms. If you want to use the Hough transform for one of your projects as a side or as part of a bigger project, you can obviously just use a library and reuse it. You don't need to build it from scratch. However, if you feel your project would be the Hough transform itself, then obviously your project would not be just calling an API and you would be done. It would be considerably more work. But if you use it as part of a bigger pipeline, just use a library. And with that, we will come to the last feature detector of today, the Harris corner detector. And the Harris corner detector allows us to find corners in an image. So far we've seen edges, we've seen straight lines, and so edges we've seen last time. Today we've seen straight lines, and now we'll come to corners. And corners are very distinctive for objects, and I'll tell you why. Imagine we are on an object, like on this calculator, and I have a pixel somewhere here where this sun is, and I move the pixel a little bit. The intensity doesn't change much. It will change a little bit, but if I just move in the neighborhood on the object, I don't get much of a change of intensity. If I move along a straight line, I will only get a big change of intensity if I move orthogonal to the straight line. So this is my straight line. If I move along the straight line, change of intensity will be minor. Only if I move left or right, maybe then I may get a bigger change of intensity. But for corners, if I'm on a corner and whatever direction I move to, I would typically get a much bigger change of intensity. So corners, they are way more distinctive than straight lines or edges, and corners are super helpful as features, which I would put then into some other subsequent step in my pipeline, like a machine learning system to detect objects. And obviously, if I apply a corner detector to an image, I would not just get that one corner, I would get a lot of corners. And calculating them is actually not that expensive. And then I have a lot of corners and I can process them further in the pipeline, as we will see next week. Now, we will see how we can detect corners. And for this, I will switch to my iPad and we'll build this together. So we will see the Harris corner detector. It's all in the slides, but I think developing it here step by step is more fun. Harris corner detector. This will be a little bit of math today, and let's see if we fully finish it today or if we complete it next week. Honestly, we'll just see how much work is left. And so the Harris corner detector does the following. Imagine I have my image, and there is some object, say in blue, and then I have a small window that I call W, so big W for now. And this is a small window. So I'm writing this here, window, oops, W, that can be shift, that small window is a few pixels big. So not just one pixel, but a few times few pixels. And that window can be shifted. So it can be shifted by D. And D is a vector, UV as a column vector, or a row vector, UV. So it's a column vector or just a row vector that we transpose. And so we can, and it's in the slides, D is sort of bold because it's a vector. And we can move our window a little bit. So we move it, if we move it, we move this by U pixels along X and along the y-axis with V. So I put this here, X and Y, something like this. So we move it along UV. So here's my U, here's my V. And if I move this, this window around, then the intensity within the window will change. And I'll show you this. So we will sum up how this intensity changes. So I have a window, and the window has a certain size and multiple pixels. And that's why this XY coming out of W means one specific pixel with XY coordinate in the window, like up here where I've just put the point. And I go through all the pixels in the window. And I have a function I, which is the intensity. So it's a grayscale image, and the intensity is, again, between 0 and 255. And before, so I will put something here in a moment in this function. And before I start moving it, I have this intensity xy. It's a value between 0 and 255. Now I have my D up here. If, so UV, if I change or move the window by U pixels in X and V pixels in Y, I get a difference. And the change UV is also small. I move this window around a little bit, and for one specific pixel in the window, XY, this intensity has somehow changed. Do you all agree with me up to here that this makes sense? Maybe thumbs up or thumbs down. Now, this change can be positive or negative, but I'm summing up all of these changes. But summing up positive and negative changes, usually that doesn't work well. And I also want to penalize large changes. So I'm squaring the change. That's a typical technique in signal processing, AI, machine learning. Squared errors, so my errors are always 0 or positive. Big errors are penalized more. And I call this error error of UV is that sum, and I'm going through in that sum all the pixels in the window. If I have a uniform patch, like before on this calculator, somewhere on the calculator, on the black plastic, these uniform patches, they will be near zero. If I just move the window a little bit on there, because there's not much change of intensity, so that error will be close to zero. But if I have very distinctive patches, such as corners, that error will be quite large. So we are interested in maximizing this. So we want to maximize this, maximize when looking for corners. Now we need a little bit of extra math in order to do the next steps. Who of you is familiar with the Taylor expansion or Taylor series? If this is something that you remember, send a thumbs up. If you don't remember, send a thumbs down. Certainly something that was taught at some point in your maths course, but we will look at it briefly. We'll do a revision because there are quite some who don't remember it. That's fine. So we need some extra math now so what I've just shown you was this, the Harris corner detector. And we will continue with that in a few moments, but we need more math. And the Taylor expression or Taylor series, what it is, it allows us to approximate a function. Say I have a function f of x, but I don't know how to calculate it directly. I can approximate it. And f of x can be approximated, and we assume that f of x can be differentiated infinitely. So it's infinitely differentiable. And it works with real numbers, works with complex numbers, that doesn't matter. And f of x can be approximated around a number a with the following series. F of a, so if we just don't know how to quantify f of x, but we know what its value is in a certain value a, then we can, around that value a, approximate the function f of x with the Taylor expansion or Taylor series. It's f of a plus the derivative of a multiplied by x minus a plus divided by 1 factorial plus the second derivative of of f at a divided by 2 factorial times x minus a squared, and we can continue this for the third order derivative. We cube here, divide by 3 factorial. This can be summarized as the following. It's the nth order derivative of f at a, where n starts at 0. So 0th derivative is just the original function at a, divided by n factorial, multiplied with x minus a raised to the power of n. So who of you remembers this or has at least seen it? Thumbs up. If you have really never seen this, maybe send a thumbs up, send a thumbs down. So thumbs up, you have ever seen it, and thumbs down, you have really never seen this, because remembering it in detail and never seen before are two different things. But it's certainly something that would be taught in the first year math. And but I know we have some exchange students, maybe visiting students. So I will say a few words and we will look at a few examples of this. And And I'm happy someone likes the explanation. And it's actually, it looks more difficult than it is. And I will show you now what this is useful for. We'll look at it with one example. And we'll come back to our Harris corner detector in a moment. So, Taylor expansion. Imagine we want to approximate cosine. We want to know how to calculate cosine of x. So we want an equation or a formula for cosine of x. And we don't know what the formula for cosine is. So this is f of x, and we want that function. We know its value for specific x, but we don't know its overall function. So what is the derivative of cosine? Let us know in the chat. That's something everyone should know. Minus sine of x. Then the next derivative, the second order derivative is, let us know, minus cosine of x. And the third order derivative is which one? Exactly, sine of x. And then the fourth order derivative is cosine of x. So, and then this keeps repeating. Now, I will write you down again our Taylor expansion. So this was something like, so f of x would be the sum where n is 0, f of n, or f where we have the nth derivative, evaluate at some value a, we'll come to this value a in a moment, divided by n factorial x minus a raised to the power of n. That's the Taylor expansion as we saw before, and we can apply this now. So we can say there's some value a, which we will come to later. So we can say cosine of x is, we start with this 0, that means no derivative, just cosine of a plus plus we take the first order derivative, which is a minus, so we remove this minus here, this plus, we put a minus there, sine of a divided by 1 factorial times x minus a. Then we do the second order derivative minus cosine of a divided by 2 factorial times x minus a squared. Then we'll come to the third order derivative where we say plus sine of a divided by 3 factorial times x minus a cubed. And we do one more, plus cosine of a divided by 4 factorial times x minus a to the power of 4 plus dot dot dot. Are you still all fine with up to here? Hope I don't have any typo. Maybe just signal if you're still with me. And now we need to find some concrete value a for which we know the value of cosine and sine. So we say we put a is 0. So then cosine of A becomes 1. The sine of A, this becomes 0. So the whole thing disappears. Cosine of, so this one here becomes 1. We divide it by 2 factorial. This becomes all zeros. And this becomes again 0. And here, this becomes a 1. So I've just simplified this a bit. And we can write it out now because this will eventually show us that, so for A equals 0, the cosine of x is 1 from before. Then this whole thing here was 0, but we have something here where the upper one is 1. So we say x squared divided by 2 factorial, this component here. So we have this 2 factorial, and here we put in a 0. So x minus 0 squared is x squared. And this one here is 0, but we then have the next one, which was this one here. So it's just in the right color, x to the power of 4 divided by 4 factorial plus dot, dot, dot. So what you have now is a formula how you can calculate the cosine. Is this something you have done before with the Taylor expansion? Maybe thumbs up or thumbs down. Okay, you can use this also for the exponential function, for lots of other stuff. And when you look up how to calculate the exponential function, there are lots of ways how you can calculate it, and the Taylor expansion is one of many approaches. And now you've seen how to do this. Obviously, plus dot dot dot, you will get better results if you expand more. And we have done this here at least for a short moment. There's a question about binomial expansion. That's something different, in fact. So it's not the Taylor expansion. Yeah. Now you're wondering what is this useful for? We need it very, very soon for our Harris corner detector. And I'll switch back briefly to the slides. So we have just studied the Taylor expansion, which is here. We've seen the example, and I hope there was no typo when I wrote it down, but you find it here definitely properly in the slide. So with the A, and then you pick a concrete value A for which you know what sine and cosine are, or the target or the functions that you're using. And you could do the same here with the exponential function or other stuff. And it turns out this can be expanded, or you can do this for several variables. This is the Taylor expansion for several variables, because now we've only used one variable here, which was x, but with our images, we're in XY, so we have 2 variables. And that's why the Taylor expansion can be generalized. I have to admit, this is something I also don't know by heart, but I found it on the internet, and I hope there's no typo in it. But we don't need it to that detail. All you need to know in a moment is that the Taylor expansion can be used in several variables, and we're going to use it in several variables to work on our Harris corner detector, but it looks more difficult than it actually is. And I will switch back to my iPad to show you this. So, so the Taylor expansion was just the excursus, and this was the Harris corner detector. And what is really key to what we are doing now is this one here, because it turns out, especially this I of x plus u, y plus v, here we can apply the Taylor expansion. And I'll show you this now. So you just need to remember this up to here. We've moved the window or the pixel in the window by uv. And we just want to apply to what I'm highlighting now in red. We want to apply the Taylor expansion to here. It's multivariable, but I'll just show you the result of what it is. So we don't need to do the Taylor expansion here step by step. But my I x plus u y plus v can be, we can apply the Taylor expansion to it, and it's I xy. Remember, I is just the intensity. So this is the first part. Plus, we have a couple of partial derivatives. So this is a partial derivative of the intensity function along x multiplied by u plus the partial derivative of the intensity function along y times v plus dot dot dot, because we want to differentiate this infinitely, but obviously we are stopping at some point, so plus for the remainder. Now, if we go back to our error function, error at uv, we can, this was the one we had here before. So in this red part, we just plug in the Taylor, what we got from the Taylor expansion for this part. We keep this minus here, so we only put, first of all, this one in. And this will be our sum as shown before, xy from the window. And we had this one, but we put in now the Taylor expanded one, which is an approximation. That's why approximately. So the intensity of xy plus the partial derivative of the intensity function along x times u plus the partial derivative of the intensity function along y plus v minus the intensity, well, just write it uniformly, of xy as this came from before, and we square the error. So what I'm putting here in red is what we got from the Taylor expansion, and here in blue, this was the term from before, this one here. Now, do you see how we could simplify all of this? If you have an idea, let us know how we could simplify all of this. If you feel you have an idea how to simplify this, maybe thumbs up, then I'll wait for you. Otherwise, I'll show it to you. So we have these two terms that I'm highlighting in green, and they just cancel each other out. So we have this intensity minus the intensity, so they just cancel each other out. And what we have left in this squared error is just those ones here. Are you still with me? Good. And now we just tidy this a little bit up and simplify it. We introduce now, we say Ix is the partial derivative of the intensity function along x, and Iy is the partial derivative of the intensity function along y. So I'll just write out this error function now. So matching this in yellow, so it's this part here. We still leave the u's and v's, but we just write this partial derivative down as we denote it as ix and iy. So we can say our error function at uv is approximately the sum of this window and its u times ix plus v times iy squared. Remember this ix, iv, they come from here. And then I still have these u's and v's from before. So these ones and this. And now I still have this square, and I can simplify this. So I can say this is my sum xy along the window. And I'm just squaring this now. So I get u squared times ix squared plus 2 u v I x I y plus v squared I y squared. So that's just simple math from school, but I don't have just an a and b in the square, but multiple objects. So this would be sort of the a and this would be the b, but eventually that's it. So it's just a squared plus 2ab plus b squared. And now you're wondering, what is this helpful for? Why have I done all of this? It turns out we can express this in matrix form. Express in matrix form. We can write the error of uv is approximately something. So we have this sum here. And this sum is good, but we can express it now in terms of vectors and matrices. We have a row vector uv, and we can multiply it with a bigger matrix that you will see in a moment, and we multiply it to the right with a column vector uv. And we have 4 elements in this matrix. One is a sum of ix squared. We have a sum of iy squared. We have a sum of ix, iy, and a sum of the ix, iy. So I have written in this matrix form just the sum from before. You can try this out at home and just multiply these vectors, this vector with the matrix and then the other vector. We can simplify this and say this here is just our vector d, but transpose. Well, I'll put the transpose in black. Because at the very beginning, we introduced our vector d, and we said it's a column vector uv or a transposed row vector. So now I have my d, which was how much I changed the window. Then this big matrix here will be called M. And here we have D again, and all in bold. Now, you're wondering, what is this useful for, I guess? Who of you remembers, because what is key now is this matrix M. We need to do something with it. Who of you remembers eigenvalues and eigenvectors? Thumbs up if this is something that you remember, or thumbs down if you don't. But it's certainly something that was also taught in your intro to math. What is it useful for? If you have a matrix A and A is an n times n matrix, then we could have a lambda, which is the eigenvalue of A, if the following holds true. I have A, so also bold here, times x is in bold, so it's a vector, is the same as lambda times x. So x is the eigenvector of A, corresponding to lambda. What does this mean? Eigenvalues, so a n times n matrix may have multiple eigenvectors, and for each eigenvector, there's a corresponding eigenvalue. There are lots of applications for this in civil engineering, in electrical engineering, in geometry. For example, if, say, we see this from a geometry perspective, I have, say, x1, x2, I have a vector, concretely my eigenvector. So the eigenvector. What happens to the eigenvector if I multiply it with its corresponding matrix? Anyone remembers this? If so, thumbs up or thumbs down. If you remember what happens in geometry if I multiply an eigenvector with its matrix. Okay, no one. One person knows. The one who raised their hand, do you want to tell us? Turn on your mic. What happens? I'll give you a second. Question is if the matrix is inverted. No, the matrix inversion is something different. If I multiply a matrix with its corresponding eigenvector, then the direction of the eigenvector does not change, and its length gets changed by the factor of the eigenvalue. So this would be the lambda then. Imagine this was my x and I multiply it with its matrix, then the direction does not change, but the length of the vector changes. And for example, if here lambda is a half, then the length of the vector would be just half. But if it's a different eigenvalue, could be 3, it's 3 times the length. It could also happen that the direction gets inverted. That's what's possible. But then the eigenvalue would be negative. But then we just flip the direction or invert the direction, but we don't change the direction otherwise. So this would happen with a negative eigenvalue. What is all of this useful for? My impression is, please confirm if you also saw it this way. When you study and there's an introduction to linear algebra, you learn about eigenvalues, eigenvectors, but you don't really know what it's useful for. Is this something that you felt when you studied this in your math introduction? You learned a concept, but you didn't know what it's useful for. I had exactly the same problem when I studied. So if I was teaching math 1 or 2, I would definitely add some applications. This is what I just said here when I showed you this on my iPad. And maybe you're wondering how to find the eigenvectors and eigenvalues. Someone unmuted. Hello? I didn't hear you. Okay. I guess this was by accident. If you're curious about how to find eigenvalues and eigenvectors, you learned this in your math introduction. I have written a few slides here and an example where you find the eigenvalues, eigenvectors. It's not further necessary to this course, and you have already learned this in your math introduction. Yet there are some examples here how to find them, and I've told you about the geometric perspective. Now, why do we need this for the Harris corner detector? If we just go back to the Harris corner detector, we used the Taylor expansion to get to this one. We canceled out the IX and we rewrote this squared error and then re-expressed the squared error as this product of two vectors, so a row and a column vector and a matrix. And matrix M is interesting because it calculates the sum of changes along X and Y in different ways. And now we can take this matrix M, it's just a 2 times 2 matrix because this calculates a scalar. So each sum just calculates a scalar. And what happens if I apply, or if I take matrix M and I calculate its eigenvalues? So matrix M from before, and I want its eigenvalues. And with the setting we have done here, we will get two eigenvalues, and we will get a so-called corner response R. And the corner response R can be calculated by multiplying, so that 2 times 2 matrix will give us two eigenvalues at the most, but for this setting, we will get two eigenvalues, lambda 1 and lambda 2. We multiply them, and then we subtract the sum of these eigenvalues squared multiplied with k. And k is a constant that you would determine empirically, so experimentally, and it's typically a small value between 0.04 to 0.06. You would fine tune this, but now we just say it's 0.04, and we would get a corner response R. And that means we have calculated this error the whole time, and this error was we have a window and we shift the window a little bit. That's the error we calculated. And to calculate the error, we finally found this matrix M, and then we calculate in this matrix M the eigenvalues for this shift of the window. So we have a window somewhere as before in our pixels, and for that window, we calculate the corner response R. And obviously, the window will be placed throughout the image later, not just in some region, but we place that window throughout later the image. And then we assume the window gets moved by a small distance UV. So for every area in the image, we calculate a corner response. And so we would have eventually per pixel, ideally, or for different areas in the image, for many of them, we would have a corner response R. And now the question is, how big does the corner response need to be so we actually have a corner there? That's something I will show you in a moment, or we already look at it now. So the corner response is a value, and probably the bigger it is, the more likely we have a corner there. But we can try to visualize this as well. Say we have this image here, and we put our window in different areas. For example, we put a window down here, and or in that area, we move a window around. We get lots of different eigenvalues. So what is plotted here are the eigenvalues in a scatter plot, lambda 1 and lambda 2. They are like spread out in this circular form. We have this one here, where we see it's spread out along one axis, but not the other one. But there are also not really corners. It's just water. Here it's some bushes. But what you would see up here is if you put your window up here in green, you would get large eigenvalues for both. So both lambda 1 and lambda 2 would be large. Whereas here, only one of these eigenvalues would be large for the red window. And a feature of your corners is if both eigenvalues, lambda 1 and lambda 2 are large. That's the distinction to find corners. If they are both small, it's probably just some bush, some water here, really no proper shape. If one eigenvalue is large, you typically have a straight line in there. But if both eigenvalues are large, you most likely have found a corner. So that's why we need to calculate the eigenvalues. It turns out computing the eigenvalue like this can be quite slow because you need to calculate the eigenvalues many, many times because you have a lot of small matrices when you keep moving your window around. There is an estimation of how you can calculate a corner response, which is just the determinant of m minus k times the trace of m squared. Who of you knows what the trace of a matrix is? It's just a small note. If you heard about the trace, thumbs up, otherwise thumbs down. Okay, one person heard what the trace is. Can you tell us maybe in the chat or turn on your mic? All the others don't know, and that's fine too. I'll just wait for you. The trace is, yes, going along the diagonal, so from the top left to the bottom right, but the trace operator doesn't mean just the diagonal, it means summing up all the elements in the first diagonal. So from upper left to lower right, you go through the diagonal, you sum up the elements, that's the trace. So this is a more efficient way how we can calculate the corner response, because always applying the proper way how to calculate these eigenvalues is quite inefficient, but the eigenvalues are helpful for understanding and visualization. Later, you would just calculate your corner response like this as the determinant of the 2 times 2 matrix plus this one here with the trace squared. So this is super fast since the matrix is just a 2 times 2 matrix all the time. And then you would need to threshold R, a threshold above which you would say there is a corner or below there is no corner. Here's another visualization for this. If both of the eigenvalues are large, you have a corner. Otherwise, if both are small, you have a uniform region. And if one eigenvalue is much larger than the other one, you would have an edge or even a straight line. Yeah, this can be applied to sample images. For example, here we have this castle, we have an image, and we get lots of corner candidates. What we need to do is the thresholding, obviously. But the way I have shown you how the Harris corner detector is built, eventually by calculating the corner response like this, it's relatively fast, much faster than this way, because for this way, we explicitly need the eigenvalues, and that's computationally slow. And so you would calculate it with the cheaper way, you would threshold it, the corner response, and you could visualize the corners here. We have lots of corners then, and corners would be used as features in the next step in the pipeline, which we are doing next week, when we look into object recognition and convolutional neural networks. Remember, next week, officially, it's a lecture-free day, but we need the lecture to do the next 2 topics so that in 2 weeks, you are prepared for the Cronus challenge. And everyone is really required to attend online the session in 2 weeks with Cronus because they spend a lot of time and resources on this. So everyone would attend. Some may not pick the Cronus challenge. I would accept that, but at least show respect to the company. A few more things about the Harris corner detector. The Harris corner detector is invariant to translation and rotation. So if you move the objects around or you rotate them in the image, the Harris corner detector would still find them, but it's not invariant to scale. That means if you zoom in or zoom out, you would get not the same set of corners any longer. And there are way more feature detectors like SIFT. SIFT is the scale invariant feature transform, a very sophisticated feature detector. But studying that alone, we would probably need the whole semester. Maybe some of you may use SIFT through a library. There's the histogram of oriented gradients, Hough, or the difference of Gaussians, and there are probably hundreds of other feature detectors. But you know now how to find edges, how to find straight lines, how to find corners. That's already a good start. And next week, we will anyway see how we can use features or how we can self-learn them. And today, you've seen lots of math. I know that. We've looked at the Taylor expansion, and now you saw what it's finally useful for, not just calculating cosine and sine, but actually simplifying your error calculation. And like this, we can break it into a smaller problem. And finally, you also saw what the eigenvalues and eigenvectors could be used for. And there's a question about the Hough detector or Hough transformation. Why were the edges detected as points as not as lines as in the first place? So I'll be happy to go back to the Hough transform. I guess what you're referring to, the edges, we have these points and not lines. This was just for simplification. When you run edge detection here, you would get way more edges, but the edges are not necessarily continuous. And with the Hough transform, we find a straight line, but here we just put a few examples so we can actually still visualize it, rather than if we put hundreds of dots here, we wouldn't see much later in here. In the real world setting, it would look like this, and you really don't see anything any longer. But here we've just simplified it a bit in this example. So today you learned, in addition, some math. You saw what Taylor expansion is useful for, what eigenvalues and eigenvectors are useful for. If you want to revise eigenvalues and eigenvectors, we have some examples here in the slides. And I know it was a very intense lecture today, also intense for me. Just before I taught the lecture, today I'm outside Frankfurt. I gave a keynote today at an event around AI and insurance and finance. So there are a lot of board members of large insurance companies here today. And I gave the keynote around lunch. Then we had lunch. And I still had to teach this course. So they gave me a very big meeting room here at a very large insurance company headquarters outside Frankfurt, where I'm teaching the course. And now I'll ride home. And I look forward to seeing you next week in the online lecture for looking into object recognition, convolutional neural networks. If you can attend it live next Thursday, that would be good. If you can't, watch the recording before the Cronus Challenge, because the Cronus Challenge will be a lot about convolutional neural networks. So you should be up to, or you should be ready to get that. I wish you a great evening. See you next week. Bye-bye.